Hello everybody, I am Dr. Punyadarshini Poonam Tripathi from Agricultural and Food Engineering Department, IIT Kharagpur. Today I will be giving a lecture for this module 2, a part of module 2 I have covered in a previous lecture, that is performance analysis of solar drying systems. Today I will be discussing about the computational modeling of the drying process. So, some of the references I have listed here that I have followed for preparation of this lecture. Now, coming to the need of modeling and simulation of the drying process, because we know that drying is one of the most energy intensive operation in the food processing industry, and at the same time it is a complex phenomenon that involves simultaneous and often coupled multi-phase heat, mass and momentum transfer phenomenon. So, during drying the physico-chemical changes occurred in the food matrix, and as a result of which these changes can affect hugely the quality of the dried product, and these changes are occurred due to the mechanism of mass transfer and rates of heat transfer within the food material. Often that transfer mechanisms takes place in an unpredictable manner. So, investigation of the physico-chemical changes occurring during drying is very important in order to achieve the proper control of the food quality during the drying process, optimization of energy consumption during the drying process, optimizing the drying process parameters, getting desirable characteristics, getting desirable drying characteristics. And in order to achieve all these characteristics in line with the drying process, a huge number of experimentations is required, because we need to customize the drying process by optimizing different process parameters at the same time to get the better quality end product. But experimentation itself requires a lot of time. It needs again costly laboratory and high end experimental facilities. So, in order to reduce this experimentation, mathematical models and computer simulation is the best technique, which basically acts as the realistic tool to describe the real scenario during the drying process. This is an effective alternative to experimental practices and represents an excellent understanding of the transfer phenomenon that can take place during the drying process, which often is neglected or which often cannot be visualized during the experimental period. So, modeling of drying process is very useful for understanding the mechanism of the physical process, and accordingly the suitable design of dryers can be attempted for providing superior performance. Generally, the drying process can be modeled using two different approaches. The first approach is the modeling that is based on empirical approach, and second one is the modeling based on principles of physics and mathematics. So, when we are dealing with this empirical approach based models, so they are basically categorized as regression model developments, models that are developed through regression analysis, and empirical and semi-empirical models to describe the drying characteristics of the food products. However, compared to physics based model, these empirical based models are easier to analyze and easier to interpret also, because it often requires some experimentation to carry out and to note down the different parameters during the experimental period, and then by curve fitting we can get the results. That means, it often gives the direct relationship between the average moisture content and the drying time, or temperature versus the drying time, which can be predictable using the experimental data set. But these models cannot define the underlying physical principles of drying, such as what is the amount of heat penetration into the food material during the drying process and what is the moisture transfer mechanism during the drying process. These intrinsic parameters cannot be well defined by these empirical models. So, they are not successful in describing the complex drying phenomenon. In this context, the physics based models are widely being employed and appreciated also. So, in physics based models, modeling requires information on the material that is to be dried and the drying media, such as the thermophysical properties of the food materials and how is the interaction with the food matrix, that is very importantly taken care of during development of the physics based model. Basically, this model define the heat and mass transport phenomenon effectively. It has a greater acceptance in the field of research and development. These are mechanism based models. So, through these models we can visualize the results for pressure variations, velocity variations, temperature distribution, moisture distribution during the different thermal processes. Now, coming to the mechanism of convective drying, as we know that during drying process from the heating medium, due to convective heat transfer, the product is getting heated up, which in turn releases the moisture from the food matrix to the surface by diffusion and again through convective mass transfer. So, in this convective drying process, basically we can see two different periods of drying can be observed: constant rate period of drying and falling rate period of drying, which is well known in the field of drying. So, here the constant rate period of drying and the falling rate period of drying is shown with regard to drying rate versus the moisture content, and we can see initially the moisture removal rate from the product is very fast, because the unbound moisture is evaporated due to the latent heat of vaporization of water, and as a result of which, as can be seen, the slope is constant and this is designated as the constant rate period of drying. And once it reaches the critical moisture content, the surface moisture removal rate is reduced and the falling rate period then follows off. So, here in this particular case of drying mechanism, we are going to attempt for the modeling technique. So, what happens during the drying? So, here drying is basically categorized as a multiphysics problem. Here coupled heat, mass and momentum transport parameters takes place simultaneously, and exchange processes also takes place with the environment, that takes place at the air and material surface or material interfaces. So, the major physics involved for development of this multiphysics model during the drying process is the heat transport parameter, mass transport parameter, fluid dynamics, structural change that takes place inside the food matrix, as well as the textural changes taking place inside the food material. And heat transfer again can be counted as convective, radiative, conductive heat transfer, with some phase change also takes place during the drying phenomenon. As you can see, this is the transport process that is being shown over here. We have the different types of liquid evaporation in terms of diffusion, capillary action, there is Knudsen diffusion also. There are different types of diffusion process for removal of moisture from the inside matrix to the surface of the food material, and again exchange process takes place from the surrounding environment to the surface of the food matrix. For example, water vapor and air, we have the convective heat transfer that is taking place, and again from the water vapor and air, as we can see, this convection is basically the convective mass transfer from the surface to the surrounding environment, whereas convective heat transfer is from the hot air to the surface of the food matrix. So, this is basically a very complex phenomenon of heat and mass transfer, which needs detailed investigation through the development of the computational models. So, for model development, basically two types of approaches are normally taken into consideration. Based on these approaches, we can classify the models as conjugated model and non-conjugated model. Non-conjugated model means when suppose we are going to dry food material, we are considering only the intrinsic properties or the thermophysical properties of the food material to be given as input parameter to the model, and then that will predict the simultaneous variation of temperature and moisture throughout the drying period. But conjugated modeling comes into picture when the surrounding environment along with the food matrix is coupled together. That means what is the temperature and the fluid flow characteristics outside the food matrix, that has to be integrated with the food intrinsic characteristics in order to develop a conjugated model. So, that will give us a real scenario of the physical phenomenon that is taking place inside the food matrix, as well as the surrounding environmental changes also can be visualized properly through the simulation. So, for model development 3 stages are normally practiced. The first one is the pre-processing stage. So, in the pre-processing stage we have to select the geometry of the food material or the dryer, that should be taken into consideration. So, for geometry selection we can select either 2-dimensional geometry or 3-dimensional geometry, that again depends on the interest of the type of problem that we are going to solve. Then we have to define the physical problem, what is the exact physical problem for which we are developing this model. We have to define the material properties, selection of physics, then we have to define the initial and boundary conditions, and very important part is the mesh generation. This development of the suitable mesh plays a very important role in convergence of the simulation results. So, nowadays more developed mesh types like polyhedral, tetrahedral, and this type of meshes can be incorporated so that they can provide the better quality or fine quality simulation results as compared to simpler meshes. So, by employing this pre-processing stage, in the processing stage we can check the quality of the mesh by changing the different types of mesh and the mesh volume and the mesh elements. Then the partial differential equations for solving the heat and mass transfer phenomenon during the drying process has to be taken care of using different modeling platforms. Then discretization of mathematical equations will be taken care during the processing stage, which ultimately helps in achieving the convergence for giving us the optimum simulation results. In the post processing stage, the numerical analysis of the results can be validated, and this validation is done with compared to the experimental results, and the results can be visualized. So, here if we develop a 3-dimensional model of a particular food material during the drying process, then a better visualization of the temperature distribution inside the food matrix can be very accurately predicted, which cannot be observed through experimentation only. So, that is why the modeling techniques in food processing has a widespread acceptability nowadays. Now, coming to the governing equations, normally for drying purpose we are using this Fourier equation for analyzing the heat exchange in an isotropic solid food material. Rho Cp del Tp upon del T is nothing but equal to dou minus Q, where rho is the density of the food solid, Cp is the specific heat capacity, then Tp represents the temperature of the food solid, and Q is the heat flux. Similarly, for analyzing the moisture migration, we can write, this is again analogous to Fourier equation in heat transfer, which we can write in terms of diffusion equation, that is basically fixed second law of diffusion, where the diffusivity term is coming into picture, and this is the basic governing equation for mass transfer, where Ci represents the concentrations and T is the time, and D effective is represented as the effective moisture diffusivity. So, considering these governing equations and specific boundary conditions, the model has to be developed. So, during the model development, again thermal properties, basically the thermophysical properties of the food material has to be taken care of. For example, the thermal properties of food product, that includes the specific heat capacity and thermal conductivity. These are the intrinsic properties of the material and represent the ability of the material to accumulate and transport heat during the process of drying. So, specific heat capacity is the amount of energy needed to increase the temperature of 1 kilogram of matter by 1 degree Celsius. A strong correlation between the food's composition and its specific heat can be represented by the relation Cp is summation of Ci into Cpi, where the Ci is the mass concentration of each constituent present inside the food matrix and Cpi is corresponding to the specific heat capacity. And again thermal conductivity, this is needed for heat conduction calculations. This property can be directly measured for a food material, and the factors affecting thermal conductivity are the composition, what is the orientation of the fiber present inside the food matrix, and what are the void spaces present inside the food matrix. So, based on this thermal conductivity values, some empirical correlations for fruits and vegetables were developed. So, this is just a generalized equation presented here, where thermal conductivity is represented in terms of 0.148 plus 0.493 into W, where W is the mass fraction of water. Some of the different transport properties of various food materials are also listed here. For model development, the input parameter to the model for moisture transfer mechanism is diffusion coefficient, where for different shape and size of food materials, the values along with the used equations are being presented here. Let us say for potato cylinder, pineapple slice, carrot slice, the diffusivity values are being presented, and again the values are calculated by considering the shrinkage phenomenon and without considering the shrinkage phenomenon. That means, during the drying process the material shrinks to a larger extent, but for simplification of the mathematical solution, most of the researchers normally neglect the shrinkage phenomenon during the drying process, but it is very important to incorporate the shrinkage phenomenon, because that gives an ideal representation of the drying mechanism, so that the dryers can be developed accordingly for suitable drying of the food materials. Similarly, mass transfer coefficient for potato cylinder, pineapples and carrots were also calculated, and the values are reported for direct, indirect and mixed mode solar dryers. Now, coming to the model validation part, for development of the model we can go for different procedures as discussed. Then after development of the model we can visualize the desired temperature and moisture migration inside the food matrix, and that model has to be validated with the experimental one. So, differences between the values predicted by a model and the experimental values can be represented in terms of mean absolute error, root mean square error and standard error. So, these are the standard statistical procedures for validating the developed model. Now, specifically if we look into the finite element model for direct, indirect and mixed mode solar dryers. So, a 3-dimensional finite element based COMSOL multiphysics software has been used for development of the model for direct, indirect and mixed mode solar dryers. As can be seen, the model geometry has been made in COMSOL multiphysics platform, and then material properties has been given to different components of the dryer. So, this is a direct form of dryer whose meshing has been done, and this is the 3D model developed and meshed geometry of direct, indirect and mixed mode solar dryer. So, this one represents for both indirect and mixed mode. If the top surface of the drying chamber is opaque, then it is designated as the indirect solar dryer, and having the transparent glass cover we can solve it as the mixed mode solar dryer, or if it is opaque it is indirect solar dryer. Now, with the help of the governing equations, here basically for development of the model, the heat transfer in solid module considering the surface to surface radiation and external radiation source feature has been considered for development of the finite element model for direct, indirect and mixed mode solar dryers at no load condition. That means, after designing of the solar dryers without any samples, the no load test has been carried out to find out the optimum performance of the dryers. So, in that regard it is very important to visualize the air temperature distribution at different locations of the dryer and to assess whether that air temperature is sufficient enough for drying the sensitive agricultural commodities. So, in that regard the material properties has been identified for different components of the dryer. For example, glass cover, absorber plate, then wall of the dryer, and boundary conditions has also been given in terms of diffuse surface, then convective heat flux from the absorber plate to the moving air, and the walls of the dryer are being designated as properly insulated. So, developing the model and then after providing the governing and the suitable boundary conditions, the temperature distribution profile in these dryers can be visualized. As can be seen in the initial stage of the experimentation, the temperature is uniform throughout, as can be shown in this first picture. So, there is uniform temperature throughout in the beginning of the test, but as time progresses there is temperature variation throughout the dryer. So, this blue color represents the coldest zone, whereas the red color represents the hottest zone or the hottest temperature inside the dryer. So, with progress of time it was observed that the beneath part is the absorber plate, which is black color, already it is painted in black color, and in the in the experimental period this black color absorber plate it is getting heated up quickly due to the absorption of solar radiation, and the air layer just adjacent to the absorber plate are red in color, that means they attain the maximum temperature, and at the same time the temperature beneath the glass cover is very less, as it is represented the cold zone in the blue color mark. However, with more progress of experimental period we can see still the temperature of the air near the absorber plate is more heated as compared to the glass cover. This is again due to the temperature variation between the absorber plate and the glass cover. So, this is a representation of temperature distribution inside direct, indirect and mixed mode solar dryers. However, it was observed that in case of indirect solar dryer, the uniformity in temperature is more or less is achieved, because the drying chamber is opaque and it is not directly receiving in solar radiation, whereas in case of mixed mode solar dryer there is temperature gradient can be observed from these simulation results. So, after development of these results, the models are validated with the experimental values, and from the statistical error analysis it was observed that both the experimental values and the predicted values are in close agreement with each other, justifying the suitability of the air temperature distribution inside the dryers using the finite element simulations. Similarly, with load, with the use of food materials inside the drying chamber, the heat and mass transfer analysis for food materials has been also carried out. So, this is a heat and mass transfer analysis during solar drying of potato cylinders, as can be seen. Then on the wear mesh plate the potato cylinders are being placed, and during the drying process basically what happens, three modes of heat transfer takes place simultaneously: convection, radiation and conduction, and as a result of which the material gets shrinked with time. So, due to this shrinkage phenomenon, it is very important to analyze the material shrinkage along with the temperature and moisture distribution during the solar drying of potato cylinders. So, in order to analyze that, finite element model was also developed for the potato cylinders by considering its geometry formation. With suitable mesh the geometry has been formulated, then heat transfer in solid module. For mass transfer, the transport of diluted species module has been incorporated with the moving mesh module for analyzing the deformation behavior of the food material. So, for governing equations in heat transfer, we have used this Fourier law of heat conduction, and the initial and boundary conditions are being provided, and similarly for mass transfer the governing equation as for fixed second law of diffusion along with the initial and boundary conditions are also being provided to solve the particular problem. And here for deformation behavior the arbitrary Lagrangian and Eulerian method is also employed to better prediction of the shrinkage phenomenon of the potato cylinders. and as can be seen, the temperature distribution profile is shown over here. Initially, as can be seen, the temperature of the sample is uniform throughout, but with experimental drying period, it was observed that during the initial stages of drying there is considerable heat penetration into the product, and the temperature gradually rises, and afterwards the temperature rise was more or less increasing in a slower fashion. So, the temperature increases from an initial value of around 25 degree centigrade up to a final value of around 42 degree centigrade throughout the drying period. And this is the temperature distribution profile at different time intervals starting from 0 to 5 hours. So, it took 5 hours to increase the temperature from 25 degree centigrade to 42 degree centigrade until the product reaches a safe moisture content of 10%, that is in wet basis moisture. Similarly, once we get the temperature from the model, that model predicted temperature is validated with the experiment, and it was observed that both are in good agreement with each other. Similarly, the moisture distribution profile of the samples can also be shown over here. As can be seen, the sample, the moisture basically from the sample is released from those surfaces which are in direct contact with the hot air as well as with the solar radiation. So, at different time intervals again the moisture values has been predicted. So, from initial moisture to final moisture it took around 5 hours, that means for removal of moisture, and at the same time the product gets shrinked. So, the shrinkage behavior as well as the moisture and temperature distribution profile can be very properly visualized from the development of the finite element model. So, here the moisture distribution profile from the experiment with the model predicted results were validated, and it was observed that the model predicted results are in close agreement with the experimental values, thus justifying the development of the finite element models during the solar drying of food materials. That gives us an idea about the intrinsic property changes of the food matrix, the internal moisture migration mechanism and heat penetration mechanism during the drying of food products, which cannot be visualized through the experimental analysis. Thank you so much.